Hello, I'm Babahan, and I'm gonna tell about two digital twins with my friends. Let's start with what was it? A digital twin or a digital replica is a virtual model of a physical asset such as a product, process, system, or a facility. Said digital replica takes and uses data from an actual physical asset to better understand and augment its performance. For example, engineers can identify the safety risks of an aircraft engine by assessing different temperatures and stresses on parts. Surgeons can navigate a digital visualization of an organ before operating on it. A digital twin of a rocket that displays its maximum wind resistance can ensure a launch in bad conditions and so on. How does digital twin technology work? Digital twin, the virtual counterparts of a physical asset, is created as the digitalized duplicate of a machine or a physical site. These digital assets can be created even before an asset is built physically. To create a digital twin of any physical assets, engineers collect and synthesize data from various sources, including physical data, manufacturing data, operational data, and insights from analytics software. All this information, along with algorithms, is integrated into a physics-based virtual model, and by applying analytics into these models, we get relevant insights regarding the physical assets. The consistent flow of data helps in getting the best possible analysis and insights regarding the assets, which helps in optimizing the outcome. And what challenges has it solved? Digital twins are powerful masterminds to drive innovation and performance. Imagine it as your most talented product technicians with the most advanced monitoring, analytical, and predictive capabilities at their fingertips. By 2018, companies who invest in digital twin technology will see a 30% improvement in cycle times of critical processes, predicts identical. Also, the digital twin technology helps companies improve the customer experience by better understanding customer needs, develop enhancements to existing products, operations, and services, and can even help drive the innovation of new businesses. Thank you. My friends gonna continue.
Who invented it? The person named Michael Graves has introduced the concept of digital twin for the first time in history. The digital twin concept gained recognition in 2002 after Challenge Advisory has hosted a presentation for Michael Graves in the University of Michigan on technology. The presentation involved the development of a product lifecycle management center, which contains all the elements familiar with the digital twin, including real space, virtual space, and the spreading of data and information flow between real and virtual space. While it's commonly thought to be developed in 2002, digital twin technology itself has actually been a concept practiced since 1960s. NASA would use basic twinning ideas during this period for space programming. They did this by creating physically duplicated systems at ground level to match the systems in space. An example is when NASA developed a digital twin to assess and simulate the conditions on board Apollo 13. Digital twin can be broken down into three broad types, which show the different times when the process can be used: DTP, DTI, and DTA. The first one is digital twin prototype, DTP. This is undertaken before a physical product is created. The second one, digital twin instance, DTI. This is done once a product is manufactured in order to run tests on different user scenarios. The last one is digital twin aggregate, DTA. It gathers DTI information to determine the capabilities of a product, run prognostics, and test operating parameters. Besides these three main types of digital twins, there is another type that occurs in the field of artificial intelligence, the Intelligent Digital Twin, IDT. Not only does this digital twin mirror information, like the types of digital twins we have already introduced, it's also capable of making predictions based on data we collect. The use of intelligent digital twins could predict how this product will behave in the near or distant future based on the current state of a product. This would avoid errors in advance and simulate the complete life cycle of a product.
And the other topic is why and how are designed. As I mentioned about the digital twins can be created for a wide range of the applications. For example, a test, a prototype, and design to assess how a product or processes will work under the different conditions and determine and monitor the life cycles. And it has three different categories. The first one is data. A digital twin requires a data about an object and processes in order for a visual model to be created that can represent behaviors or states of the real world items or procedures. This data may relate to the life cycle of the product and include design specifications, production processes, or engineering informations. It can also include production informations, including equipments, materials, parts, methods, and quality control. The other one is modeling. Once the data has been gathered, can be used to creating computational analytical models to show operating effects, predict states such as PEGU, and determining behaviors. These models can prescribe actions based on engineering, simulations, physics, chemistry, statistics, machine learning, artificial intelligence, business logic, or objectives. These models can be displayed via 3D representations and augmented reality modeling in order to aid human understanding of the finding. Last one is linking. The findings from digital twins can be linked to create overviews, such as by taking the findings of equipment twins and putting them into a production line twin, which can then inform a factor scale digital twin. By using linked digital twins in this way, it is possible to enable smart industrial applications for a real-world operational developments and improvements. The relationships with the digital twins in the assemble are typical. The first typical is hierarchical, and the other one is peer-to-peer and associational. And the next one, this photo is the explain this assemble types, and this last one is the benefits. The benefits of the digital twins differ depending when and where it is used. For example, using digital twin to monitor existing products such as a wind turbine or oil pipe can reduce maintenance burdens and save many millions in associated costs.
I will give you some examples about digital twin from practice. It's developed in such industries like energy, hospitality, retail market, urban environment, and healthcare. In the energy sector, digital twins are used to create virtual wind farms For example, like each wind turbine on a computer based on terrain and wind data from the rings, and then use that wind to design the most efficient type of the turbine in physically in the real world. I mean, once the turbine is fired, its virtual counterpart begins collecting and analyzing environmental data. Moreover, it's possible to create a digital patient model of a human body that gives an idea of the state of health. For example, Philips has developed the application which creates a retailed 3D image of the human heart from ultrasound images. On the other hand, the hospitality sector digitalization has affected visitors, halls, and kitchens, and the company is testing various options, therapy reducing staff turnover, and creating a better visitor experience. Moreover, in the retail market, digital twin uses an approach that collects detailed real-world data from the physical retail environment and then uses it to better understand the customer behavior and actions. So these tips are the examples from the practice of non-manufacturing companies of the usage of the digital twin. How it's impacted to the real world, I mean, how digital twin impact us. The main impacts are like five. The most impacts of digital twin are visibility. It's the ability to take a general look at the entire production and understand what and where deviates from the specified parameters. Like motivating employees to do their job effectively, like simulation tools, like within the simulation tool, a digital twin assists in optimizing workflows. And it's a tool for making informed and operational management decisions. And moreover, you can simply build production inside a computer space and evaluate how processes will change in different conditions for the real world. One example is the Vinum platform, which is Java-based cross-platform was built. And Vinum is the interactive digital twin, which allows us to simulate virtually any object in a virtual environment, like anything we see with our eyes. I mean, from a specific physical product, physical group, mechanical or technological process to production lines. Working with a digital twin doesn't require stopping the equipment. You can look inside the production at any time, at any place, at any moment. At the same time, the digital twin includes not only a 3D object with technical characteristics, but also information about the environment and operating conditions, about interactions with other objects, as well as predictive analytics data. The information obtained from the equipment can be used, for example, in assessing bottlenecks, technical conditions, operation process, and such things like it's like this.
Merhaba hocam, merhaba arkadaşlar. I'm İlham Akhmatov, student of Business Administration Department, taking course selected topics in Production and Operation Management. Now I'm going to presenting you application area used for digital twin. The digital twin of the product includes geometric and structural model of the object, a set of calculated data for parts, assemblies, and the product as a whole. Mathematical models that describe all physical processes occurring in the product. Information about the technological processes of manufacturing and assembly of individual elements and the product as a whole. Product lifecycle management system. The digital twin is used at all stages of the product lifecycle, including design, production, operation, and disposal. At the stage of preliminary design, variants of a computer model of the product under development are created to assess and select possible technical solutions. At the technical design stage, the option chosen at the previous stage is finalized and refined using element models. The resulting model of the product allows you to take into account and optimize the interaction of all elements, taking into account the operating modes and environmental influences. It can already be called the digital twin of the product being developed. At the manufacturing stage, the developed model helps to determine the required manufacturing tolerance to achieve the required characteristics and ensure the failure-free operation of the product throughout the entire service life, and also allows you to quickly identify the causes of faults during the testing process. At the operational stage, the digital twin model can be finalized and used to implement feedback in order to make adjustments to the development and manufacture of products, diagnose and predict malfunctions, improve work efficiency to identify new consumer requests. So what about digital twin as a service in Industry 4.0? We are living in the digital era, and the trend for individualization has been moving beyond digital modeling, simulation, and the digital twinning since Industry 4.0 emerged. Fiber, physical plus cyber, refers to blending online digital experiences with physical ones over cyberspace, satisfying user experience. Fiber indicates a blended concept with DNA mutually involving in physical and cyberspace. A fiber has joined life in physical and cyberspace, which can grow in an iterative, incremental process using its digital origin. Therefore, individualization increasingly becomes fiber by taking to the best aspects from physical, digital, and cyberspace. So this figure illustrates the principal concepts this reference model defines. Digital twin as a service is a service to enable access to digital twin capabilities, where the access to fiber is provided using augmented interface across physical, digital, and cyberspace. The role of DTS is to offer capabilities and act as a service provider. Any fiber with needs that make use of services are referred to digital twin enabled service consumers. This reference model is an abstract framework for understanding the relationship among the three axes, consists of unifying concepts and relationships altogether across physical, digital, and cyber domains for providing shows that DTS. The main drivers for the reference architectures are facilitating in the manageable growth of large-scale digital twin systems, facilitating provisioning on cyberspace and efficient use of resources using different integration levels through an agile life cycle. The value of DTS is providing a simple, scalable paradigm to realize the importance of mass individualization. Indeed, DTS is scalable because it makes their own cyberspace. Thank you for your attention.